The idea of a fighter jet isn't just speed or firepower. It's control of the sky in the most extreme situations. Some aircraft are built to turn tightly, others to strike from distance, but a rare few are designed to dominate vertically. That's where this story begins. There was a jet that redefined what climb performance could look like, pushing beyond the limits most pilots were trained to expect. In fact, most planes struggle to climb effectively. This one could go nearly straight up into the sky, and that capability wasn't just impressive, it changed how air combat could be fought. The idea of a fighter jet is often reduced to speed, maneuverability, or firepower, but in reality, one of the most decisive factors in air combat is energy. Not just how fast an aircraft can go, but how quickly it can convert that speed into altitude, position, and tactical advantage. This is where certain aircraft begin to stand apart. Among them, the F-15 Eagle and the MiG-29 Fulcrum represent a category of fighters that pushed performance into a realm that, for earlier generations, would have seemed almost impossible. Both aircraft emerged during the Cold War, a period defined not just by political tension, but by rapid technological escalation. The skies became a proving ground for engineering philosophies that prioritized dominance in every dimension of combat. For the United States, this meant creating a fighter that could guarantee air superiority under almost any condition. For the Soviet Union, it meant building an aircraft capable of countering that dominance with agility, raw power, and resilience. The result, in both cases, was a machine that could do something few others could: climb at angles so steep they appeared to defy conventional flight. The phrase climbing straight up is often used casually, but in aviation, it has a very specific implication. It refers to an aircraft with a thrust-to-weight ratio at or above 1, meaning the engines can produce as much or more thrust than the aircraft's total weight. Under these conditions, the aircraft is no longer relying primarily on aerodynamic lift from its wings to stay airborne. Instead, it's being pushed upward directly by engine thrust, almost like a rocket. This fundamentally changes how the aircraft can move through the sky. For the F-15 Eagle, this capability was not an accident or a secondary feature. It was central to its design. Powered by twin Pratt & Whitney F100 engines, the aircraft was engineered with a specific goal in mind: to ensure that it could outclimb, out-accelerate, and outfight any opponent it might encounter. The result was a fighter with a thrust-to-weight ratio exceeding 1 under combat conditions, allowing it to perform near vertical climbs immediately after takeoff. The MiG-29 Fulcrum approached the same goal from a slightly different perspective. Soviet designers emphasized a balance between raw thrust and aerodynamic agility. Equipped with twin RD-33 engines, the MiG-29 was capable of dramatic high-angle climbs that became a signature feature in air shows and operational demonstrations. While its exact thrust-to-weight ratio varied depending on loadout, it was still capable of entering steep climbs that pushed the boundaries of what most pilots expected from a fighter jet. What makes these aircraft remarkable is not just how they can climb steeply, but that they can do so rapidly and repeatedly under real operational conditions. This is not a one-time demonstration or a carefully staged maneuver. It's a core part of how the aircraft functions in combat. When a pilot pulls back on the stick and engages afterburner, the jet responds with an immediate surge of thrust, converting forward momentum into vertical motion in a matter of seconds. This capability changes the geometry of air combat. Traditional dogfighting often focused on horizontal maneuvers, turning circles, and maintaining speed. But with a high thrust-to-weight ratio, a pilot can break away from that plane of motion entirely. Instead of turning to evade or pursue, the aircraft can simply go up, forcing the opponent to react in a way that may not be sustainable given their own performance limits. The visual impact of this cannot be overstated. From the ground, it appears almost unreal. A fighter jet accelerating down the runway suddenly pitches upward, nose pointing toward the sky, and continues climbing at an angle that seems too steep to maintain. The afterburners glow intensely, leaving a shimmering trail of heat distortion behind, as the aircraft ascends rapidly into thinner air. For observers, it looks like defiance of gravity. For pilots, it's a carefully controlled application of physics and engineering. Understanding why this matters requires stepping back from the spectacle and looking at the underlying principles. Climb performance is not just about how quickly an aircraft can gain altitude, but how effectively it can control its energy state. Energy, in this context, is a combination of speed and altitude. A fighter with more energy has more options. It can engage, disengage, reposition, or dictate the terms of the encounter. The F-15 Eagle was designed with this philosophy at its core. Its ability to climb rapidly allows it to gain a positional advantage early in an engagement. By moving to a higher altitude, it can convert that altitude into speed when needed, diving toward a target with increased velocity. This gives it both offensive and defensive flexibility, making it difficult for opponents to predict or counter its movements. Similarly, the MiG-29 Fulcrum uses its climb performance as part of a broader strategy focused on agility and close-range engagement. While it may not match the F-15 in every parameter, its ability to rapidly change altitude and direction allows it to create unpredictable flight paths. This unpredictability is itself a form of advantage, forcing opponents to react rather than act. What emerges from this is a shift in how fighter jets are understood. Rather than being limited to speed or maneuverability in a traditional sense, aircraft like these operate in a three-dimensional battle space where vertical movement is just as important as horizontal positioning. The sky is no longer a flat area, but a volume of space where altitude can be gained or lost as quickly as direction can be changed. This is the foundation of what makes vertical climb capability so significant. It's not just a technical achievement or a visual spectacle. It's a fundamental change in how air combat can be conducted, and to fully understand its impact, it's necessary to look more closely at the mechanics behind it, particularly the concept that makes it all possible: thrust-to-weight ratio. At the center of vertical climb capability is a concept that, while simple in definition, has profound implications in practice. Thrust-to-weight ratio is exactly what it sounds like: the amount of thrust an aircraft's engines can produce compared to the total weight of the aircraft. If the thrust equals the weight, the ratio is 1. If the thrust exceeds the weight, the ratio is greater than 1. And it is at this point that conventional assumptions about flight begin to change. In most aircraft, lift generated by the wings is what keeps the plane in the air. The engines provide forward motion, and the wings convert that motion into lift. Climbing requires a balance between thrust, lift, and drag. The aircraft must maintain enough forward speed for the wings to generate lift while gradually increasing altitude. This is why most planes climb at relatively shallow angles. If they attempt to climb too steeply, they lose forward speed, lift decreases, and the aircraft risks stalling. However, when thrust exceeds weight, the aircraft is no longer entirely dependent on lift from the wings. The engines themselves can provide enough force to push the aircraft upward, even at a very steep angle. In extreme cases, this allows the aircraft to climb vertically, with the wings playing a secondary role. The jet is effectively being propelled upward by sheer engine power. For the F-15 Eagle, this is achieved through a combination of powerful engines and relatively low structural weight for its class. The twin F-100 engines generate enormous thrust, especially when afterburners are engaged. Afterburners work by injecting additional fuel into the exhaust stream, creating a secondary combustion that dramatically increases thrust. This comes at the cost of fuel efficiency, but in combat, performance takes priority over endurance. The MiG-29 Fulcrum uses a similar principle, with its RD-33 engines providing the necessary thrust to achieve high climb rates. While its design places a greater emphasis on maneuverability and short-range performance, the underlying physics remain the same. When the engines are producing maximum thrust, the aircraft can pitch upward at steep angles without losing control. To visualize this, imagine two fighters starting at the same altitude and speed. One has a thrust-to-weight ratio below 1, while the other exceeds it. When both attempt to climb, the first must do so gradually, maintaining forward speed to generate lift. The second can simply point its nose upward and continue accelerating vertically. Within seconds, the difference in altitude becomes significant, and with it, the tactical advantage. This advantage is not just about reaching a higher altitude faster. It's about how quickly an aircraft can change its energy state. In air combat, situations evolve rapidly. A pilot may need to disengage from a losing fight, reposition for an attack, or evade an incoming threat. The ability to rapidly gain altitude provides an option that may not exist for less capable aircraft. Another important aspect of thrust-to-weight ratio is acceleration. High thrust allows the aircraft to regain speed quickly after a maneuver. This is critical because aggressive maneuvers often bleed off speed, leaving the aircraft vulnerable. A fighter with strong acceleration can recover that lost energy and remain effective in fight. The combination of high climb rate and strong acceleration creates a feedback loop of advantage. The aircraft can climb to gain altitude, convert that altitude into speed during a dive, and then use that speed to climb again. This cycle allows the pilot to control the pace and geometry of the engagement, forcing the opponent into a reactive position. It's also worth noting that the thrust-to-weight ratio is not a fixed value. It changes depending on the aircraft's configuration, including fuel load, weapons, and external stores. A fully loaded fighter carrying heavy payloads will have a lower thrust-to-weight ratio than one in a lighter configuration. This means that pilots and mission planners must consider these factors when preparing for combat. Despite these variations, aircraft like the F-15 Eagle and the MiG-29 Fulcrum are designed to maintain high performance across a range of conditions. Their engines provide a margin of capability that allows them to retain strong climb performance even when carrying weapons and fuel necessary for real-world missions. The result is an aircraft that is not just capable of impressive demonstrations, but one that can apply those capabilities consistently in operational scenarios. Vertical climb is not an isolated trick or a moment of spectacle. It's a manifestation of deeper design philosophy that prioritizes energy control, flexibility, and dominance in a three-dimensional battle space. Understanding thrust-to-weight ratio explains how certain aircraft can climb nearly straight up, but it doesn't fully explain why that capability matters in combat. To see its real significance, it has to be placed in the context of how air combat actually works. Modern fighter engagements are not just about turning faster or flying higher. They're about controlling energy, position, and timing in a consistently shifting environment. In this environment, climb rate becomes one of the most important variables a pilot can control. It directly affects how quickly an aircraft can gain altitude, but more importantly, it determines how effectively a pilot can reposition during a fight. This is where aircraft like the F-15 Eagle and the MiG-29 Fulcrum begin to demonstrate their true advantage. Air combat can be understood as a competition for positional dominance. Pilots are constantly trying to place their aircraft in a position where they can engage the opponent while minimizing their own exposure. Traditionally, this was visualized in two dimensions, with aircraft maneuvering horizontally to get behind each other, but in reality, the flight takes place in three dimensions, and altitude is just as important as direction. Climb rate also plays a defensive role. When a pilot detects an incoming threat, the ability to rapidly change altitude can be the difference between evasion and interception. By climbing or diving aggressively, the aircraft can alter its trajectory in ways that make it more difficult for a missile to maintain a lock. This is especially important against advanced guidance systems that rely on predicting the target's path. What makes vertical capability particularly powerful is how quickly it can be applied. In a matter of seconds, a fighter can transition from level flight to a steep climb, changing its position in the battle space dramatically. This rapid change can disrupt the opponent's situational awareness, creating moments of confusion that can be exploited. There's also a psychological dimension to this. Pilots train extensively to understand the limits of their aircraft, but when faced with an opponent that can climb more aggressively, those limits are tested. The knowledge that the opponent can simply go vertical and reset the engagement adds pressure, forcing quicker decisions that may not always be optimal. Historically, this advantage has been demonstrated in numerous training exercises and operational scenarios. Aircraft with superior climb performance consistently show an ability to control engagements, even when other factors are comparable. This does not mean they're invincible, but it does mean they have more options available at any given moment. One of the clearest examples is the intercept mission. When an unidentified or hostile aircraft is detected, fighters are scrambled to intercept it as quickly as possible. Time is critical, and so is altitude. The faster a fighter can climb, the sooner it can reach the altitude of the target, or position itself above it. Aircraft like the F-15 Eagle were specifically designed with this role in mind. Upon takeoff, the pilot can engage afterburners and initiate a steep climb almost immediately. Instead of gradually ascending, the aircraft gains altitude at a rate that significantly reduces the time required to reach the target. This can be the difference between intercepting the aircraft before it reaches a critical area or arriving too late. The MiG-29 Fulcrum performs a similar role in air defense scenarios. Designed to operate from forward bases, it can be launched quickly and climb aggressively to meet incoming threats. Its ability to operate in these conditions reflects a broader doctrine focused on rapid response and localized control of airspace. In the end, the image of a fighter jet climbing nearly straight up is more than just a striking visual.